So this video here is going to be the last kind of chill one. We're just going to go over and cover a few kind of miscellaneous concepts and backgrounds we're going to get before we get into universal covering algebras, all that fun stuff. So our first topic here is going to be extensions. Once again, this is a concept that very well could end up being familiar to you that we're just going to be generalizing to the algebras. So we're going to let A and B be Lie algebras over the same field K. Now we're going to find an extension of B by A is an exact sequence, I believe it's an exact sequence so I changed capitalization. Let's just have these be lowercase. Why not? A is going to go into G by some morphism lambda, and G is then going to go into B by some morphism mu. So G is going to be a Lie algebra also over K. Lambda is going to be the injective homomorphism. Mu is going to be a surjective homomorphism. And because this is an exact sequence, I believe that's how it works. We have that the image of lambda is going to equal the kernel of mu. And we're also going to call this image of A in G, we're going to call it N. And so N is going to be called the kernel of the extension. And this is the same kind of construction as you see in like ring theory and that kind of thing. Just generalized to Lie algebra. And of course we have that lambda is an isomorphism of A onto N, and we similarly have of mu being an isomorphism of G divided by N onto B. A quick reminder from ring theory, this doesn't make G any sort of product of A and B. For For example, we have a natural example of the integers going by the doubling map into themselves, then going into by the natural quotient map to z over 2z. And we have here that the image of our first z in what RA is here is going to be the even integers in the middle here, which are of course going to be the kernel of the quotient map by 2z. But z is of course not equal to any sort of product between z and z over 2z, as evidenced by the fact that 1 in z over 2z, 1 plus 1 is 0 in that context, and that is never going to transfer over into z. And this is, in this original case, we have that g is an extension of b by a. And so we say that two extensions are equivalent. I'm not going to write out all the little diagrams here, but the key idea here is we have two extensions of b by a with all of the relevant morphisms here. And we have a morphism from G into G prime by what we're going to be calling F. And we say that these two extensions are equivalent if this is commutative. That is, lambda prime equals f composed with lambda, and mu is mu prime composed with f. Now, we actually don't need to assume bijectivity. As we see. First off, for injectivity, so if we let x in G such that essentially that's in the kernel of f, then mu of x, keep in mind as above, because the diagram is commutative, we get this is mu prime of f of x. Because x is in the kernel, this inner fx is going to go to 0, and since mu prime is also a homomorphism, this whole thing is going to give us 0. So the kernels are going to line up here. And so we get that x equals lambda y for some y in A. And the reason for that, because remember, the image, the kernel of mu is the image of lambda. So since the kernels of f and mu line up in this sense, since x is in the kernel of f, it has to be in the kernel of mu, and therefore in the image of lambda. And from that, we get that lambda prime of this y equals f of lambda y, which is f of x, which by assumption is 0. And this gives us y equals 0, so that x is also equal to 0. And that's just because these maps, lambda and lambda prime, have to be injective. And of course, the only function, the only element, it's going to get sent to 0. That should be obvious here. And we also can prove surjectivity. Because we have that mu, which is also equal to mu prime composed with f, is surjective by assumption. And so we can find that's not really the right set of words to use. And so we have that g prime, every element in g prime can be written as the sum of f in g plus lambda prime in A. Just keep in mind yeah. Sometimes I'm learning this as I write it, so I don't always have like an immediate explanation for what's going on here. And we also have that f of g is inside of f of lambda of A which is by composition just lambda prime of A. And thus we have the diagram as defining an equivalence relation. And this gives us our sense of equality over extensions. Extensions. There's more than one of them in all of math. I like how I try to backspace to make things neater and then I just don't. Alright. Now, proposition. I don't think, well, we don't have much space. Let's just go to a new page here. Let A lambda G mu B be extension in the obvious way of B by A with a kernel we call N. That's the setup. There's two parts of the proposition. Part 1, if there exists a subalgebra M of G supplementary to N, which, if I recall correctly, means that M plus N, like the sum inside of G, gives you all of G, which might not be the correct definition, but that's the idea. That it's kind of, together they look at all of G. Then we have that mu restricted to this M is an isomorphism from M, obviously, to B. And if we set rho, what letter is this? Is this nu? If we set nu to be the inverse of this isomorphism, which is going to take me a minute to draw out properly. And then we have that mu is a homomorphism of B into G, and it says that mu composed of nu is the identity automorphism, which I think is just true by definition, right? And also, this second part itself even seems trivial. The only part that isn't just like definitionally true in this is that the restriction of mu to M is an isomorphism, but even then, given like the isomorphism theorems and the kernel, I think that is pretty obvious. They don't bother giving a proof here. And we have the converse case, where nu is a homomorphism of B into G such that the composition of mu with nu is the identity of B, its identity map. And then we have that nu of B is supplementary to our kernel in G. As I said, A is pretty much entirely automatic. So we have nu of B I guess I'm not going to use that word we. is a subalgebra of G with G as the direct sum of VB and N. Okay, it doesn't seem like you did a lot of work there in their proof, but I will take it. Alright. Now on to some more definitions. We have our same example extension. Once again, that includes the kernel of N. And this extension is called inessential, or alternatively trivial, if there exists a subalgebra, or alternatively an ideal, of G supplementary to our kernel N in G. This extension is called central, if N is inside the center of G. Alright. So, what can we do with this? So if the extension is trivial, you let M be supplementary to, I guess we have to specify that it is an ideal, as we get by definition. Supplementary to N in G, as the definition outlines. Then we get that G is canonically identified. They use that very fancy phrase with the Cartesian product, with the Lie algebra product of M and N. And thus A times B. Conversely, for Lie algebras A and B, A cross B is a trivial extension. And they say of A by B, but I'm thinking you can do it either way, given how it looks to be set up. I'll do a little proposition here. They don't list it as one, but I'm going to write it. an inessential central extension is trivial. So with the above setup, that is, G is a Lie algebra with an ideal. Okay, what? Let's write that out. G be a with n inside the center of G, ideal of G, and M a subalgebra of G supplementary to N, inside G, of course. Then the bracket of the sets, M and G, the bracket of the algebras, that is. Well, since G can be split into supplementary M and N, we can split the set into those sets. And of course, since N is inside the center, this is just going to, that term is going to disappear. This equals 0 as N in the center. And so this is just gives you M, bracket of M with itself, the derived algebra, which is inside M. So M is an ideal of G, of course. Alright, and so with that we can move on to our next topic here, which is semi-direct products. So here we aim to describe all inessential extensions of B by A. So let G be such an extension, that is an essential extension of B by A. And so we can identify A with an ideal of G, B with a subalgebra of B, with an A and B being supplementary inside of G, and I believe and identify the module G with the module A times B. Now what this means is that the bracket itself of G isn't necessarily just going to be component-wise over A cross B, A times B, but we have everything else, like our sum and our scalar product. And of course, in this context, we're working with modules instead of vector spaces. As I said, we're going to flip back and forth between the two a lot. A lot of times, just don't worry about it. This works with vector spaces as well. For all, they chose the worst possible. Okay, we're gonna go cap. No, you know what? I'm gonna do whatever I want. We're gonna use C and B. Don't know why. And so we're gonna let phi of C be the restriction to have the adjoint representation in B to A, which I believe is just the adjoint. No. Okay. So I'm sorry, they're using two B's here, and they technically have different typefaces, but they're virtually indistinguishable, so I gotta figure out which one they mean here. And this is a derivation of A we also have the generated mapping of arbitrary phi in B to the restriction of its adjoints to A is a homomorphism of B into the Lie algebra of derivations of A. So this is our first bit of setup. We also have for A, I'm going to go A hat and A prime in A, B hat and B prime in B. We have, and then there's going to be A hat and B hat. So essentially we're taking the Lie bracket of two elements in the product. And we often just write, since it's clear where each term is coming from, we often just write these Cartesian products as like sums instead. And so we have, by linearity, you can FOIL this all out. A hat with B prime plus B hat with A prime plus B hat with B prime. Is there a way for me to select this and copy it over so it's like easier to follow? Maybe, but I don't know how to do it. And of course we had, as a reminder, we had a hat and a prime, which is we're just going to leave alone. And we had the derivation of a hat with b prime. But I'm just going to write it all out again here. I mean, it's easy enough to just cycle through all the 4 combinations. Now, we're going to put this back into the Cartesian product. A hat and a prime are 2 elements from A, the algebra. So that we're just going to leave alone, like this. Now, we're going to skip ahead to the 3rd component here, b hat with a prime. Now the way we're going to define this Lie bracket between these two is we're going to be sending, just keep in mind, we have the adjoint representation of b hat, and we're taking the restriction to a prime. So the natural definition here is going to be that whole dealio of b hat acting on a prime. And then of course, since Lie brackets are antisymmetric, the other way it works the same, except with the sign reversed. Keep in mind, phi is the restriction of the adjoint representation to A, so trying to swap the places of A and B doesn't make much sense since the function still won't be over B. And of course, our last component stays in its set of B, so that gives us no issues. So, with that way of transferring the bracket over from one subalgebra to the other, we get no issues. But how does this work for just 2 random algebras that we don't know the parent of? So, let A and B be Lie algebras. This time they're just unrelated, random ones. They're both over the same, I guess in this case, a ring, K. And the function phi, phi sending element C. Function, I guess, phi with the domain of B and the codomain of the algebra of derivations of A. Some element phi getting sent to phi of C. And this is, of course, a homomorphism by definition. And so we can now justify defining the Lie bracket on the, keep in mind it is a module, A cross B, and it looks as above, just with these phis no longer being the restriction of the adjoint representation to the other subalgebra, or I guess in that case it would be an ideal, but instead we just have it be some derivations that we're defining. So this bracket is alternating and bilinear just basically structurally, because alternating... Oh, okay, I didn't know you could do that. That's actually nice. Alternating just because, like, of this change in signs between the phis and the Lie brackets, and bilinearity, much the same way. Now, so the only question left is, does this satisfy the Jacobi identity? And the way we do this is we use that sum notation before. We just have to check. There's 4 cases. So essentially we're asking, I'm going to carry over that same notation, does j of x, y, and z equals 0? If x, y, and z are all in A or all in B, we just get it as the brackets are just the brackets on that side. So that leaves us with 2 other cases. And these should be lowercase because I cannot keep my notation straight. If x and y are in if x and y are in A and z is in B, then the bracket of x with the bracket of y and z is going to be x, and what is the bracket of y and z? Well, z's in B, so that gets sent to some derivation, which then acts on y. This is going to be a minus sign since z is on the right. And so that gives us some element of the bracket like this, and this is going to be some element of A. Y with the bracket of z and x. This of course is going to work in much the same way, but we no longer have to flip things over, so we don't get the sign change. And this is also going to be in A. And in our last case, z of x and y. Keep in mind the bracket of x and y is still going to be inside of A, and so z is going to be a derivation acting on that, which, as we recall, is going to be bracket of z on x with y plus the bracket of x with phi of z on y. And the term on the left is the negative of the middle term by anti-symmetry. The term on the right is the negative of the term at the top by the fact that it has minus sign in front of it. And in the other case, we have x from A and we have y and z from B. In this case, with the bracket of x with the bracket of y and z, Well, this bracket, once again, is just an internal bracket of b. And so this is just going to be the negative phi of the bracket of y and z on x. Once again, this is an a. I'm pretty sure they're all going to be an a, so maybe I didn't need to write that. The bracket of y on the bracket of z and x is the bracket of y on phi of z acting on x, which is going to be phi of y on phi of z of x. And z, of course, is going to give us x and z of x and y. It's going to be z, you can probably tell where this is going by now, on negative phi of y of x. And so this is going to give us negative phi of z, phi of y of x. Everything is linear, so we can pull that minus sign out to the front. And thus it satisfies our condition with the observation that the phi of y and z is equal to phi yz, phi y composed with phi z minus phi z composed with phi y. So this term on the left, and term on the right, we have from the bottom two, and we're then subtracting the equivalent of the left on the top term, and so we get 0. And thus we have the Jacobi identity in every possible permutation. Alright. Oh. How much longer do we have to go? Quite a ways. We will finish off this one section and then I think we'll call it here. Otherwise we'll be here for another like 30 minutes. So we have from this new semi-direct product that the mapping, which is just gives you the second component, is a homomorphism. Okay, well, I'm just gonna write this a bit more elegantly than they had. We thus have the function from A which essentially is putting a 0 in the left to G, and the function which just returns the right component. Is an extension with all the necessary components as you'd want. Which is called said to be canonically defined by A, B, and this function phi, which sends elements of B to derivations of A. And the mapping from B to its side is an isomorphism of B to a subalgebra of G. Keep in mind A is the ideal, B is the subalgebra. And this is supplementary to n in G, because keep in mind our kernel is just going to be all of A. Right? It's going to be the elements, more specifically, it's going to be the image of A, the elements of the form A comma 0. And this is, of course, elements of the form 0 comma B, so the inessentiality, the supplementary, is pretty trivial. And so the extension is inessential. Alrighty. I'm just going to write here that n is equal to elements of the form A0 in G. I guess, yeah, that's probably the best way to write it, as sets. If A is identified with n, I think they call these lambda and mu, as always, so I'll go write those in here at the bottom. By lambda. And we'll of course call this new. And B with new B, that's kind of funny. Under new. I guess they're both under by, same thing. Let's keep it consistent. Then for A hat in A, B hat in B, the adjoint of B acting on A is going to be, by everything we saw above, it's going to be the bracket of B with A, which is just going to be phi of B on A. When phi sends everything to 0, G is just the product. And that's defined in the usual way with the bracket acting component-wise, as you can tell. For arbitrary phi, though, phi is the not phi, G is the semi-direct product of A the semi-direct product of B by A. And we're going to do some propositions with that and some examples and one more topic next time. So it looks like we're going to be still in this zone for a little while.